Welcome to qnawire.
Okay, so the question is asking us to determine the lowest frequency sound that can be used to detect. Okay, but in order to find out the frequency, we need to figure out the lambda, which is the wavelength first, since the speed of sound is given, which is 340 meters per second. Let's put it down as a known condition. So V is equal to 340 meters per second. Okay, and we know the diameter is 3 millimeters for the de detector. So now first we need to figure out the lambda. Okay, so the equation that describes the diffraction in this case from this question is sine theta equal to 1.22 lambda divided by d. So we know d, which is 3 millimeter, but it seems like we don't know sine theta. But let's take a look. So since we know d, the exact value of the d, that means the d is fixed, it's constant, so it doesn't change. So in order to get a largest wavelength, why we need to get largest wavelength is because we know. Let me write down. So frequency is equal to velocity divided by wavelength. So let's take a look. Since we know the velocity, which is 340 meters per second here, so let's say it's constant because it doesn't change. So if lambda is large, it's really large, okay? So when lambda is increase, that means the frequency need to decrease. So if a lambda, which is the wavelength, is the largest, then the frequency should be the lowest. So we need to make sure we get the largest lambda, the largest wavelength from all these calculation equations. So since in this case the lambda must be the largest, must be enormously huge. So let's rewrite the equation here. Sine theta equals 1.22 lambda divided by d. Okay. So lambda is increasing until it reaches the largest value it can get. D is fixed. Since we know the exact value of d, which is constant, it's 3 millimeter. Okay. That means sine theta must increase as well. Okay. Because sine theta and 1.22 lambda here is positive related. Once increase, another one must increase as well. So in order to get a largest wavelength, we need to get a largest sine theta value as well. And the largest sine theta value is 1, which means when theta is equal to 90 degrees, and the sine theta will equal to 1, the largest value you can get. Let's say max. Okay. So that means, let me go to the second page. That means sine theta must equal to sine 90 degree, which will give us 1. So 1 is equal to 1.22 lambda. Let's say lambda m, which means, let's say lambda max, since it's more clear to show what I mean here. So it's equal to 1.22 times lambda max equal to d. And we know d is 3 millimeter. So we can just do some calculation here. And so d is equal to 1.22 lambda max. Okay. So lambda max is equal to d divided by 1.22, which will give us 3 times 10 to the negative 3 meters, since 1 millimeter is 10 to the negative 3 meter, divided by 1.22. And that will give us, that will give us 2.46. Let's see, 1, 2, 3 times 10 to the negative 3 meter, which is 246. Let me see. I try to convert it to nanometer, so let's take a look. 10 to the 9. It will be it'd be quite huge. Let me see. So you become 2.46 times 10 to the power of 6 nanometer. Ooh. Okay, and that's the largest wavelength we can get from these equations. So now we can figure out the lowest frequency we can get. So let's say f minimum, which is the lowest frequency, which is just equal to v divided by lambda max, the largest wavelength, and that will give us 340 meter per second divided by lambda max, which is 2.46 times 10 to the power of 6 nanometer. But you know what? Let's just leave it in meter. So it's 2.46 times 10 to the negative 3 meter. Since it's meter per second, so we can cancel out a unit easily from this way. Then we'll get frequency. The lowest frequency is equal to, let's take a look. One, 3.8267 hertz. 1, 2, which is about 1.38 times 10 to the power of 5 hertz. And that's the lowest frequency we can get for such a detector to detect. Thank you.